SwayamPrabha. Digital India. Educated India.
Good morning, friends. When I come to high speed, you will see one term is very popular, which is sweep. That is, if you see an airplane, before I draw the diagram, let us see if this is a wing and there is a flow here, right? And the aerofoils are here, like this, staggered. These are only, I am showing the cross section, okay? We all understand the aerodynamic characteristics over the wing is decided by the flow along the chord, the flow normal to the leading edge. Primarily that is. So now if it is 1 Mach, theoretically speaking, then this is also 1 Mach, so already supersonic, it is coming to a supersonic, transonic, supersonic, they go close. What is our aim? Our aim is that can you do something, even if free stream is around 1, the normal component is less than 1. Then the free stream may be around 0.95 near transonic, but normal component to the aerofoil, if it is less than 0.95, then I'm happy. Okay? So I have reduced the effective Mach number, which will decide the aerodynamic characteristics. So what is done? Theory is very simple. You stagger the aerofoil in this fashion. Instead of, now see, flow is coming like this. Let's say this is M, Mach number. What we have understood? It is a normal component, which is M cos lambda. That is, if this is the wing, this is the lambda, sweep angle. That is, aerofoils are stacked like this. The contouring is done like this. So that is what I am drawing. Now what will happen? Since for lambda finite, cos of this is less than 1. That is, if lambda is finite and greater than 0, then cos lambda will be always less than 1. If it is less than 1, then that means m cos lambda for a finite value of lambda will be less than m. That is, if let's say it is 0.98, then depending upon the lambda you have chosen, this normal component can become 0.95. So you are reducing the transonic effect seen by this aerofoil. So you are reducing the drag and increasing the effectiveness in a sense that whenever you are near a sonic Mach number, shock wave will come, that will interact the boundary layer. Not only loss of lift, but also there is a drag, vibrations also may come. So you are avoiding that in a very loose way, if I try to explain, because since we have not talked about anything high speed. So this is the way a sweep back has become very popular. But if you see somebody shows you a platform like this, and the aerofoils are staggered like this, then definitely it is not sweep back. Because for sweep back, the aerofoil has to be staggered like this. The flow is coming like this. So the first case is not at all a sweep back, it is simply a taper ratio case. See, another important thing you must understand, these are the aileron, and generally there is a tendency for us to fly at higher angle of attack to get the maximum advantage. Now the problem there is, as I try to fly at high angle of attack, there is a possibility of a stall. So what is done? One way is that you ensure such that the root stall first, so the pilot gets a warning, and then he brings the airplane out of the stall condition through elevator and aileron, primarily aileron. So what is done is, one way is we give a geometric twist at this portion that is on the in the tip, you put a negative angle, slight negative angle, so that even if here it is around 12-13 degrees, which is closer to a stall, the area here is seeing less than 12 or 13 by 2 degrees, so that this will not stall, but this will stall. Now we can recover. Another way is you select aerofoil such that the aerofoil has the characteristics here to having a smaller stall angle compared to the aerofoil here. That is, one of the ways it could be handled is by adjusting the T by C of the aerofoil here. Let's say this aerofoil will be stalling at 12 degrees, this aerofoil will stall at around, let's say, 13 degrees. So even if there's a stall situation, this portion will stall, and this will give a warning to the pilot, and he can control the airplane through aileron. So this is also possible. So these are the small things which we need to take care in the design and make sure that you have enough authority given to the pilot to control it, to recover it from one point to the other, to ensure that he goes from one equilibrium to another equilibrium. If that is important, it is equally important also that from a adverse situation, it should be able to drive the airplane back to a normal situation. And that itself is called really a good design, because you cannot expect everything will go nice, the climate will be the way you wanted. There will be a situation where the airplane goes into a distress, but the good design should have taken those things in mind, and the pilot should have enough bandwidth to take the airplane out of that distress. Suppose we want to now try to understand few important design aspects of a high-speed airplane. How do I distinguish high-speed airplane and low-speed airplane? We say if the Mach number is less than 0.3, we will treat them as a low speed, and beyond 0.4, the beginning of high speed starts. Typically, the transport airplane, say Boeing 747, Airbus, all these series, they'll be flying somewhere around 0.85, 0.8 to 0.85, around that Mach number, so that we get a better time advantage in terms of reaching a point. But designing such an airplane, especially the wing, we need to be a little careful. Remember one thing, as far as drag is concerned, we know the major component of drag is skin friction drag. This is because of friction or skin friction. Some pressure drag because of flow separation, right? Also, when I go to high speed, reaching near transonic or supersonic, the compression will start and there is a formation of shock wave. If there is a formation of shock wave, we know that a lot of energy will be lost, and that equivalent drag we say dW, or W is for wave drag, right? Now we are designing an airplane, let's say at Mach 0.85. Cruise Mach number is 0.85, or let's say 0.8. We need to be very careful about few things. One is, typically if you see the CD versus Mach number plot, typically it goes like this. Up to let's say 0.6 to 0.7, all the aerodynamic coefficients or parameters, derivatives, almost they remain constant with Mach number. Whole story begins beyond 0.6 or 0.7, and there is a region here where there is a sudden rise in, sharp rise in CD. So there is a typically we call Mach divergence or drag divergence Mach number. To be more precise, drag divergence Mach number. That is where at some point, some Mach number, there is sudden increase in the drag profile. So a good designer will ensure that when he is flying, he is not flying at drag divergence Mach number, number one. So we need to plot CD versus Mach number and find out what is the drag divergence Mach number. If it is 0.85, we will not design the airplane for cruise at 0.85. We will try to see something different than 0.85, maybe 0.75, 0.78. So we have to avoid this drag divergence Mach number, number one. Number two, we have been discussing, this is the wing, let's say, and as the flow comes here, the flow accelerates here, right? Do you recall this? Because if I take a controlled surface like this, the area reduces, the velocity will increase to maintain the same continuity of flow. So there is an increase in the Mach number or increase in the speed. Now suppose somewhere here it is 0.8 and we have wrongly designed the aerofoil, and what happens at certain point, because the speed is going to increase, at certain point it is reaching Mach number equal to 1. Then there is a sudden increase in the drag profile. So we need to know what is that Mach number, what is that free stream Mach number corresponding to which for the first time in the aircraft the local Mach number goes to 1, and that is called critical Mach number. What is this critical Mach number? I repeat, this is critical Mach number. It is the free stream Mach number, which is definitely not 1, less than 1. It is that free stream Mach number corresponding to which some point on the aircraft for the first time reaches Mach number 1. So that corresponding Mach number is called the critical Mach number. Okay? It so happens that if free stream is 0.85, you find here Mach has become 1 because flow is accelerating. So we need to ensure that this Mach critical or critical Mach number should be as high as possible. So how that is done? We know by now, instead of putting a rectangular fin or rectangular wing, we will be giving sweep to this wing. Okay, the aerofoils will be like this. So what happens? If this is the free stream Mach number, the normal component to this leading edge of the aerofoil will be always m cos lambda. Lambda is this angle, we call it sweep angle. So as lambda is greater than 0, the Mach number seen by the leading edge of the aerofoil is less than the free stream Mach number. So we can give, by giving appropriate sweep angle, we can go on increasing the critical Mach number, right? This is one of the primary reason why we give sweep back to an airplane. But as I have told you that nothing comes free, the moment I give a sweep, since the normal component to the aerofoil is less than free stream Mach number because it is m cos lambda, so the lifting property, lifting characteristics of the lift now generated will also reduce because now it is m cos lambda. Okay? So that is the penalty you give. However, through analysis you could see the total drag reduction is relatively more compared to the loss in the lift. But there is an optimal angle you have to operate, or design should take care of all such issues in detail. You must be aware, you can go for a Google search, you could see the Russian MiG-21 bis. It has a variable sweep. That is, initially sweep is almost 0, and then as it increases speed, it introduces a sweep back, right? That is where it tries to optimize the aerodynamic efficiency. But doing that, you should also understand you have additional load of mechanisms which could reliably do this at all times, number one. This also amounts to the increase in the weight, and increase in weight always have an adverse effect on the performance. So designer has to do all this sort of a systematic, sensitive analysis and find out an optimal or near optimal solution, right? In the design of wing and its layout, you will also see few configurations which may draw your attention, which should at least help you asking a question why this wing is like this. For example, if this is the fuselage, I can have a wing which are like this, which is called high wing. I can have an airplane which are like this. These are called mid wing. I can have airplane where like this. These are called low wing. If I compare 1, 2, 3 among them, the high wing is laterally more stable. What is the lateral stability means here? I am going like this straight, and because of some disturbance, the airplane has banked like this. Lateral stability means, again I am talking about static stability, so it means the moment this is disturbed like this, it should generate initial tendency to come back to its original bank angle. Okay? But how it is done? For longitudinal case, it is through the horizontal tail. For directional case, it is through the vertical tail. But for lateral, how does it happen? Please understand. What happens if there is a disturbance? The airplane will side slip like this. As it side slips, there should be some surface which should generate a force and try to take it back. If I have such surface available in the airplane, then I should be able to make it statically stable in lateral mode. So with this understanding, study the high wing case. In high wing case, let me explain. This is a typically, I am trying to represent a high wing case. Now, if there is a bank like this, what will happen? Because of this lift vector tilted now, it will try to side slip like this. As it side slips like this, air will gust in here, and that will give a pressure which will translate it into force and moment, and will try to turn it back. So because of high wing, there is a initial tendency to come back to the original bank angle. So it provides lateral static stability. Suppose it is a low wing like this. Assume this is the fuselage. Then what will happen? As it banks, it side slips, but now the air pressure will act on this top surface, it will further turn it back, further bank it down. That means it doesn't have any lateral static stability. That is why when we are having a high wing, it possesses lateral static stability. This doesn't, this is unstable, and this is mid-wing in between. But suppose there is a compulsion that you have to go for a low wing. So what do you do? What is the option? Option is, okay, no problem. Instead of installing the wing like this, I'll install the wing like this. And this angle, this is called dihedral angle. You could see that giving a dihedral like this will do exactly the same thing as the high wing. As it banks like this, it side slips. Because the surface is like this, it will roll it back. That is, if I try to explain you, let's say this is the dihedral angle, one wing. As there is a bank, it side slips. So air will gust in here and give a force, it will turn it back, right? So giving a dihedral, actually you are making it laterally statically stable. Okay, clear? So you should not get worried if you see some dihedral is given. You should also understand one thing, that the aspect ratio of wing is always greater than aspect ratio of tail. Typically, if it is 10 to 12, or let's say 8 to 12, it is 3 to 4 or 5. What is the reason? Question is, what is the reason? We know that if aspect ratio is high, then the induced drag component will be less, because for infinite it is 0. That means as aspect ratio is higher and higher, goes higher and higher, the downwash at the wing goes on reducing. If aspect ratio is small, then downwash at the wing is large. So now see, this is an airplane. Tail, and this is the wing. Its aspect ratio is more, so downwash is less. Suppose the airplane somehow has come near the stall, let's say 12 degree or 13 degree, let's say. Okay. Now what will happen? the wing will see 13 minus some downwash angle, which is very small because we have put high aspect ratio. But same 13 degree now, the tail will see much less because tail will have its own downwash, which will be pretty high because the aspect ratio is less. That means even if the wing goes into stall, the tail will not go into the stall because of downwash due to tail itself. So that is why we keep always aspect ratio of the tail lesser than aspect of the wing, so that even if the wing stalls, my tail is here, which will not go into stall, will try to help me out by giving a moment, and I try to come down, and I'll be very happy coming out of stall. So this is also one of the observation you must have. You will also see that if I have got a wing like this, high aspect ratio wing like this, to reduce the induced drag, we put some plate here, and we call it a winglet, right? Winglet. So that physically stops the interaction of higher pressure and lower pressure. So whatever is to be formed will have now almost, it will be diminished, right? But suppose you are putting this winglet, there is a penalty you give because there is some drag because of the winglet itself. Okay? So you have to again optimize it. There is another way of handling this situation you will find. If this is the wing will be raised like this. In continuity, it is raised like this. Okay? This is also doing almost something like this, but in a very continuous manner. Only problem of such high aspect ratio wing and this sort of a configuration is they become very sensitive to wind. That is why whenever we launch our glider, we go for a ride, if there are wind, appreciable wind, we will not really go for flight that day because it becomes very, very sensitive to wind, right? So when you design an airplane, I hope we'll be taking, if you require, a course also on aircraft design explicitly. Before that, we are planning to have a course on aircraft stability and control, which is our regular course in third semester. And when we go step by step, we'll see that little knowledge about this will help you to raise questions in your mind. How do I model it? How do I create a database so that my designers can utilize it and conveniently create a platform where pilot feels very comfortable? Okay? Thank you very much.